Right now, as you are watching this, the summit of Kilauea volcano on Hawaii's Big Island has inflated by 1.2 meters since the last eruptive episode ended in late February. Scientists at the United States Geological Survey's Hawaiian Volcano Observatory published an analysis on August 1st, noting that, based on the current rate of ground inflation measured by tiltmeters at the summit, the accumulated uplift will reach the threshold range of 1.2 to 1.5 meters, the range at which the previous 4 inter-eruptive pauses ended and new eruptions began, sometime between August 4th and August 11th of 2026. That window opened today. The instruments are reading elevated. The SO2 output from the summit vents has risen to between 500 and 800 metric tons per day over the past 2 weeks. Micro-earthquake swarms at 2 to 4 kilometers beneath the Halemaumau crater are occurring at a rate not seen since the days immediately before February's eruptive episode began. The Hawaiian Volcano Observatory has moved the eruption alert level for Kilauea from advisory to watch. What that means in practical terms is that the volcanologists who have monitored this volcano continuously since 1912 believe they are watching the final stages of the magmatic system's recharge cycle. Drop a comment right now. Have you ever witnessed a Kilauea eruption in person, or do you live on the Big Island right now? Tell me what the monitoring signals feel like from inside the island. If you want to be the first to know every time something like this develops, subscribe. It is completely free. A thumbs up also helps enormously. Let us go for 5,000 likes on this one, so the algorithm pushes it to the people on Hawaii's Big Island who are watching the sky right now. Today, we are going to break down exactly how scientists put a timing window on a Hawaiian volcano eruption, what the current monitoring signals mean, and what the difference between a summit eruption and what happened in 2018 means for the communities on the east side of the island. No guessing, no dramatizing, just the facts, the science, and the real stakes. Now, let us get into it. To understand why scientists at the Hawaiian Volcano Observatory can put a timing window on Kilauea with a precision that would be impossible at most of the world's other volcanoes, you need to understand what makes Kilauea one of the most studied volcanic systems on Earth and why the eruption forecast published on August 1st is grounded in one of the most complete, continuous monitoring records in the history of volcanology. The Hawaiian Volcano Observatory was established in 1912, making it one of the oldest continuously operating volcano observatories on Earth. In the 114 years since, it has never stopped monitoring Kilauea. The seismic network, the GPS ground deformation measurements, the tiltmeter array, the gas chemistry stations. These instruments have been recording Kilauea's behavior through every eruption, every repose period, every intrusion event, and every period of elevated unrest across more than a century of continuous data. That dataset is the foundation on which the August 1st forecast is built, and it is the reason that the forecast carries more scientific weight than a volcano observatory issuing a similar statement would carry at a less monitored system. The specific mechanism behind the August 1st forecast is the relationship between inter-eruptive summit inflation and the timing of the next eruptive episode. Beginning with the eruption cycle that restarted after the 2018 East Rift Zone eruption drained the summit lava lake, HVO scientists have documented a remarkably consistent pattern in Kilauea's summit behavior. Each inter-eruptive pause follows the same sequence. After an eruptive episode ends and lava drains from the Halemaumau crater lake, the summit deflates briefly, then begins a sustained inflation trend as magma refills the shallow reservoir system beneath the summit. The total inflation accumulated between the end of one eruptive episode and the beginning of the next has been measured across the 4 most recent complete cycles at between 1.0 and 1.5 meters of total summit uplift, measured at the tiltmeter array at the Halemaumau rim. When the accumulated inflation crosses that threshold range, the system is, in mechanical terms, full. The pressure in the shallow magma reservoir has exceeded the resistance of the rock above it, and new lava breaks through. That changed fast after the February 2026 episode. The February 2026 eruptive episode began on February 8th and ended on February 28th, lasting exactly 20 days. During those 20 days, lava filled the Halemaumau crater floor to a depth of approximately 14 meters and produced SO2 emissions at peak rates exceeding 2,000 metric tons per day. The episode ended when the lava supply from the shallow reservoir dropped below the threshold needed to maintain active surface flows, and the summit began its post-eruption deflation phase. By March 7th, the deflation had reversed, and the summit was back in inflation mode. By May 1st, the accumulated inflation since the February 28th end of the episode had reached 40 centimeters. By July 1st, it had reached 85 centimeters. By August 1st, it had reached 1.17 meters. The trend line, if extended, crosses the lower bound of the forecast threshold range, 1.2 meters. On approximately August 4th, it crosses the upper bound, 1.5 meters, on approximately August 11th. That is the window. It opened this morning. But here's the thing about Kilauea's eruption windows that makes the August 1st forecast both uniquely credible and genuinely uncertain at the same time. The 1.0 to 1.5 meter threshold range is derived from 4 complete cycles of data. 4 cycles is not a large statistical sample. The variability between those 4 cycles, each ending at a different point within the range, and each preceded by slightly different sequences of microseismicity and SO2 buildup, means that the window is probabilistic rather than deterministic. The forecast is not a prediction that an eruption will begin between August 4th and August 11th. It is a statement that the probability of an eruption beginning during that window is substantially elevated relative to the average probability at any other point in the recharge cycle. HVO scientists have been careful to state that the eruption could begin before the forecast window, if the current micro-earthquake activity accelerates and creates new pathways for magma, or after the window. If the system requires more total inflation than previous cycles before the reservoir overpressure is sufficient to initiate a new episode. But the probability distribution is centered on this week, and the elevated SO2, the shallowing seismicity, and the watch level alert designation all support the conclusion that this week is when it is most likely to happen. To understand exactly why Kilauea can be forecast with this level of precision, and why most of the world's volcanoes cannot, you need to understand what Hawaiian volcanoes are and why they are fundamentally different from the stratovolcanoes that have been the subjects of most previous videos in this series. Kilauea is a shield volcano. Shield volcanoes are the most voluminous volcanic structures on Earth. Broad, gently sloping mountains built up from millions of individual lava flows over hundreds of thousands of years. They look nothing like the classic cone-shaped stratovolcano images most people associate with the word volcano. Mount St. Helens, Mount Rainier, Mount Vesuvius, Campi Flegrei. These are all built by explosive, gas-rich magmas that produce thick, vacuous lava flows and, when conditions are right, catastrophic pyroclastic events. Hawaiian shield volcanoes are built from a fundamentally different kind of magma, basalt, which is low in silica, low in dissolved gases, and low in viscosity. Basaltic lava flows rather than explodes. It moves at speeds ranging from a brisk walk to a slow run, rather than the hundreds of kilometers per hour of a pyroclastic density current. That difference in magma chemistry is the reason that Hawaii's volcanic disasters are measured primarily in property loss and displacement rather than mass casualties, and it is the reason that Kilauea's eruptions can be forecast with a kind of probabilistic precision that would be impossible at a silica-rich explosive system. The geometry of Kilauea's shallow plumbing system is also unusually well understood compared to most volcanoes, because the HVO has been imaging it with seismic wave tomography for decades. The primary shallow magma reservoir beneath Kilauea's summit sits at approximately 2 to 4 kilometers depth, the same depth range as the current earthquake swarm, and it is connected to a secondary reservoir system at approximately 8 to 12 kilometers depth via a complex of vertical magmatic conduits. The rate at which magma moves between these two reservoir levels is one of the quantities that USGS scientists measure indirectly through the rate of summit ground inflation. When the deep system is supplying the shallow reservoir actively, the inflation rate is higher. When the supply rate drops, typically during or shortly after an eruptive episode drains the shallow reservoir, the inflation rate decreases. The pattern of alternating high supply and low supply periods and their relationship to eruptive activity is the pattern that 114 years of data has revealed and that the August 1st forecast is built on. The Hawaiian Islands themselves are the surface expression of one of the most remarkable geological features on Earth, a mantle hotspot, sometimes called a mantle plume. A hotspot is a point in the Earth's mantle where unusually hot material rises from deep in the planet's interior and melts through the overlying tectonic plate. Unlike volcanoes at subduction zones or spreading centers, a hotspot is stationary. But the tectonic plate above it is not. As the Pacific plate moves northwest at approximately 70 millimeters per year, the hotspot burns through new sections of the plate in sequence, creating a chain of volcanic islands that get progressively older to the northwest. The Big Island of Hawaii, directly above the hotspot today, is the youngest and most volcanically active. The Maui Island chain is next. Then Molokai, Lanai, Oahu, home to Honolulu. Then Kauai. The Hawaiian Islands are a conveyor belt of volcanic real estate, and the Big Island is where the factory is currently running. Kilauea, on the southeastern flank of Mauna Loa, is the most active volcano on the current hotspot. It has been erupting almost continuously in some form since 1983. The sustained supply of basaltic magma from the hotspot to Kilauea's shallow plumbing system is what makes the eruption cycle predictable in a way that a stratovolcano's unpredictable magma recharge from a subduction zone cannot match. The magma supply rate at Kilauea has been measured at approximately 5 million cubic meters per year. That is the rate at which the hotspot delivers molten rock to the shallow reservoir. When the reservoir is being filled at a known, relatively constant rate, and when the total volume required to fill the reservoir to the eruption threshold can be inferred from the ground deformation measurements, the forecast becomes a straightforward calculation. Volume in divided by volume required to reach threshold equals time to eruption. That is, in its simplest form, what the August 1st HVO forecast is doing. The precision that the USGS Hawaiian Volcano Observatory has achieved in this calculation is the result of 114 years of watching one volcano refill and erupt across dozens of complete cycles. Kilauea is the best understood volcano on Earth precisely because it erupts so often. Every eruption is a data point. Every repose period is a calibration opportunity. And every time the forecast works, or doesn't, the model gets refined. But here is the contrast that the 2026 forecast window requires understanding in depth. The eruption expected to begin during the August 4th to 11th window is forecast to be a summit eruption, lava returning to the Halemaumau crater floor within Hawaii Volcanoes National Park. Summit eruptions at Kilauea are spectacular, scientifically invaluable, and, for the communities of Puna, Kona, and Hilo on the Big Island, relatively non-threatening in terms of immediate lava flow risk. The park is closed to visitors during active eruptions, lava viewers gather at the exclusion zone boundary, and the primary impacts on the broader island are volcanic smog and sulfur dioxide air quality effects that can affect respiratory health across the windward side. Summit eruptions are what Kilauea does most of the time. They are the default. The 2018 eruption was not a summit eruption. It was a lower east rift zone eruption. And the distinction is critical for understanding the risk spectrum that Kilauea's communities live with. In May of 2018, a magnitude 6.9 earthquake struck the south flank of Kilauea, destabilizing the volcanic system and sending magma not upward toward the summit, but outward and downward into the lower east rift zone, the underground network of cracks and conduits that extends from the summit along the southeastern flank of the volcano toward the Puna district on the coast. 24 fissures opened in the residential neighborhoods of Leilani Estates and Lanapuna Gardens over the following weeks. Lava fountains reached heights of 80 meters. Lava flows covered 35 square kilometers of the Puna district. 716 homes were destroyed. Kapoho Bay, a sheltered coastal inlet lined with tide pools, coral reef, and vacation rental properties, was completely filled with lava, a bay erased from the map in a matter of days. Approximately 30,000 people experienced evacuation orders at various points during the 3.5-month crisis. The total economic damage exceeded $800 million. The August 2026 forecast window does not anticipate a repeat of 2018. HVO scientists have found no evidence of magma movement into the East Rift Zone. The seismicity, ground deformation, and gas emissions are all centered on the summit system. The probability distribution for the expected eruptive episode places summit activity as the strongly dominant scenario. But HVO has also been explicit in its public communications that the initiation of a summit eruption can, under certain conditions, trigger seismicity on Kilauea's south flank that could evolve into a rift zone intrusion event. The 2018 eruption was triggered by exactly that mechanism. It is not the forecast scenario. But it is on the probability distribution, and it is the scenario that the communities in Lower Puna are watching for alongside the volcanic activity indicators. What makes the Puna community's relationship to this forecast different from the reaction of a typical American community to a volcanic watch designation is the lived experience embedded in the community since 2018. The $800 million economic loss from 2018 included not just the 716 destroyed homes, but the elimination of an entire agricultural district's productive capacity. The papaya, macadamia, and anthurium farms that had taken years to establish in the Puna region's rich volcanic soil. The fishing grounds at Kapoho, built on the diversity of the reef ecosystem in the bay, are gone. The vacation rental economy of the Kapoho coast, which provided income to hundreds of families, is gone. The Leilani Estates and Lanapuna Gardens neighborhoods, built by middle-class and working-class Hawaiian families who had invested their life savings in land parcels on the Big Island's affordable eastern side, are gone. What the 2018 eruption took from the Puna community was not just property. It was the economic foundation of a neighborhood that had taken decades to build. That is the reference experience through which Puna residents are interpreting the current watch level designation, and it is why the watch level there carries more weight than the same designation would carry in a community without that memory. What scientists at the Hawaiian Volcano Observatory are monitoring in real time, as the forecast window is now open, is a specific set of signals that would indicate which of the two scenarios, summit eruption or rift zone intrusion, the current episode is moving toward. The ground tilt at the Uekahuna tiltmeter, the primary summit deformation instrument, is the most direct indicator of whether magma is moving toward the summit or toward the rift zone. When the tilt is inflating steadily and symmetrically around the summit caldera, Summit eruption is the likely pathway. When the tilt begins to show asymmetry, with the south flank tiltmeters responding faster than the summit instruments, that is the early signal of rift zone involvement. The current tilt pattern as of this recording is symmetric and summit-centered. There is no current indication of rift zone involvement. That picture could change in hours. The earthquake swarms being recorded at 2 to 4 kilometers below the summit are also being watched for depth migration. Magma moving from the deep reservoir into the shallow reservoir is accompanied by earthquakes that migrate upward in depth as the magma rises. A downward migration of the seismic swarm, or a new cluster of earthquakes appearing along the east rift zone trend, would be the signal that the intrusion pathway has changed. The current swarms are stable at 2 to 4 kilometers depth and geometrically consistent with summit pressurization. Keep an eye on the sulfur dioxide output from the summit vents over the next 72 hours. The SO2 at the summit has been running at 500 to 800 metric tons per day during the current pre-eruptive buildup. In the 48 hours before each of the previous 4 eruptive episodes in the current cycle, the SO2 output showed a step increase. Not a gradual rise, but a rapid jump, to values exceeding 1,200 metric tons per day. That step increase has consistently preceded the onset of surface lava activity by between 12 and 36 hours. It is the most reliable short-range eruption indicator that HVO has documented across the current eruptive cycle. The communities most directly affected by the immediate impacts of a summit eruption are the residents and businesses in the Kau and Kona districts on the leeward side of the island, where the volcanic smog produced by summit eruptions, called VOG, concentrates under typical trade wind conditions. VOG is primarily sulfur dioxide and sulfate aerosols that cause respiratory irritation, headaches, and reduced visibility. During sustained summit eruptions, VOG concentrations in some leeward communities reach levels that the Hawaii Department of Health classifies as unhealthy for sensitive individuals: children, elderly residents, and people with asthma or other respiratory conditions. The Hawaii Emergency Management Agency will issue air quality advisories for the leeward districts as soon as summit surface lava activity is confirmed. The communities on the windward side, Hilo, Pahoa, and the Puna district, face different and more varied hazards depending on whether the eruption remains at the summit or evolves toward the east rift zone. For a summit-only eruption, the primary Puna concern is acid rain. Sulfur dioxide from the summit vents mixing with trade wind moisture and falling as mildly acidic precipitation over the windward slopes. This is a chronic, manageable hazard for the existing plant life and property, not an acute emergency. For an east rift zone event, the 2018 scenario becomes the relevant reference. Lava flows moving at variable speeds through whatever neighborhoods and agricultural lands are in the flow path. Here is what the science leaves us with, and we have to be precise. Does the August 1st forecast mean that Kilauea will erupt between August 4th and August 11th? No. It means the probability distribution for the next eruptive episode is centered on this window based on the accumulated inflation, the seismic indicators, and the gas chemistry. And it is derived from a data record that covers 4 complete previous cycles. It is the most scientifically defensible eruption timing forecast that has ever been published for any volcano in the world, and it is still probabilistic. The eruption could begin before the window closes. Today, tomorrow, or this weekend. It could slip past the window if the system requires more total inflation than any of the previous 4 cycles. And the character of the eruption, summit only versus rift zone involvement, cannot be determined with certainty until the lava is actually moving. What HVO and Hawaii Emergency Management would want every Big Island resident and visitor to know is simple and specific. If you are in the Puna district and you receive an evacuation order or a lava flow warning, do not wait to see how serious it is. 2018 established that lava flows in the lower east rift zone can travel from fissure to neighborhood in hours, not days, under the right conditions. The roads out of lower Puna, primarily Highway 130, are limited, and the 2018 experience showed that traffic congestion on the single evacuation route can extend evacuation times dramatically. Have a plan, have a bag ready, and execute the plan when the order comes rather than when the lava is visible from the driveway. For summit eruptions, which is the forecast scenario, the practical action for Big Island residents is monitoring air quality through the Hawaii Department of Health's air quality dashboard and, for sensitive individuals, being prepared to stay indoors with air filtration on high during periods of elevated VOG. Drop a comment and tell me, are you on the Big Island right now? Are you watching the instruments? What are you seeing? Let us go for 5,000 likes and get this in front of the people in Puna and on the leeward side who are checking the HVO website every hour today. See you in the next one.